Hello, good afternoon, one and all. So, are you getting my voice? Hello, all. So, are you getting my voice? Am I audible? Okay, no problem. Yes, we will continue our lecture. Today, in morning lecture, we have started our new chapter. That is chapter number 7. That is implementation of OMT. And from that, we have studied the 2 3 points. Okay. So, the use of programming language and database system and object oriented style. Okay, these are 2 points we have covered. So the remaining points we will see that feature of object oriented languages and applications of OMT like object diagram compiler and computer animation, and after that we will see that the case study of hotel management system, and second one is the course management system. Okay, all these points we are going to cover. So before learning this, first of all, we will take the review. So what we covered in the morning lecture, and then after we will see that. Okay. So the first of all, we have gone for the introduction. Again, the implementation using programming language. So in the programming language, we studied about the some concepts like traditional languages, and again our object-oriented languages. So again, we saw that what are the major differences between traditional languages and again the object-oriented languages. So after that, we saw that what is the implementation using a database system. Okay, that also we have covered RDBMS, and we saw that object-oriented style. So how it could be. Okay, the object-oriented style we have saw that the reusability, extensibility, robustness, and again programming in the large. Again, in detail, we have studied about the reusability. So, very detailed study we have done about the reusability. That is the kinds of the reusability, style rules for reusability, and again using inheritance. Okay, all these we have covered already. Now, the next one is the extensibility. So, what is the extensibility? Is that the most software is extended in the ways that its original developers may not expect. Hmm. So the guidelines for reusability enhance extensibility as well. In addition, the following object-oriented principles enhance extensibility. That is encapsulate classes, hide data structures, avoid traversing multiple links or methods. Okay. Why classify operations as public and private? And after that, we studied about the robustness. Okay. You should strive for efficiency in writing methods, but not at the expense of robustness. Okay. So this also we studied in detail about the robustness. And after that, the programming in the large. So what does it mean? So the programming in the large refers to writing large complex programs with teams of programmers. Okay. That is called as the programming in the large refers to writing large complex programs with the teams of programmers. Human communication becomes paramount on such projects and requires proper software engineering practices. The following guidelines should be observed. First one is do not prematurely begin programming. Keep methods understandable. Make methods readable. Okay, use exactly the names as in the object model. And after that, we saw about the class description. This is about the class description, how the class you are going to describe. Okay, the class name, circle, version, description, superclass, ellipse, features, public attributes, public methods. Okay. In the public attribute center, point, location of its center, a radius, a real, its radius, public methods. Okay. The public methods are draw window, draws a circle in the window, intersect the line, set of points, finds the intersection of a line and a circle, returns set of 0 to 2 points. Okay. The area, real, calculates area of circle, perimeter, real, it calculates the circumference of circle, private methods, none. Okay. This is about the class description, and this is about the method description, how you are going to describe the method. See, in case of the description, we are not going to write the program, but we are going to write how it could be. Okay. The method description is that some method name is circle, intersect line, and description is that given a circle and a line, finds the intersection, returns a set of 0 to 2 intersection points. Okay. If the line is tangent to the circle, the set contains a single point, and the inputs are self circle, circle to be intersected with line, the line to be intersected with circle, and it returns a set of intersection points. Set may contain 0, 1 or 2 points, and the side effects are none. The errors, if the figures do not intersect, returns an empty set. If the line is tangent to the circle, then it returns the tangent point. If the circle's radius is 0, then it returns a single point if the point is on the line. Okay, this is about the method description. And finally, we saw that the operation description. So what is the operation description? Again, the operation description is that operation intersect the line, the set of points, the origin class, geometric figure, and the description is that it returns a set of intersection points between the object and the line. The set may contain 0, 1 or more points. Each tangent point only appears once. If the line is collinear with a line segment in the figure, only the two endpoints of the segment are included. Okay. And the status is that abstract operation in the origin class must be overridden, and the input is that self geometric figure to be intersected with line, and the line to be intersected with circle. Okay. And it returns a set of intersection points. Set may contain 0 or more points. Side effects none. And the errors, if the figures do not intersect, returns an empty set. If the line is collinear with a line segment in the figure, the set includes only the endpoints of the segment. And if the figure is an area, then its boundary is used. Okay. This is about the operation description. Means in that way we can describe the class, we can describe the method, and again we can describe the operation here. Now the very important, very familiar point is that already we are knowing this object oriented language features. What are the object oriented language features are there? So we'll see that what are the object-oriented language features. So the object-oriented languages vary in their support of advanced object-oriented concepts. Okay, and there is no single language that matches all styles and meets all needs. Very important because every language is having their different features, the different characteristics they have. So that's why there is no single language that matches all styles and meets all needs. Okay. Now, interpreted languages are useful for rapid prototyping. The rapid prototyping means what? The rapid prototyping is that whatever the softwares are there, the softwares we are going to deliver it very fast by using the rapid prototyping, but may not be adequate if you have stringent timing constraints. And there is no point in building your own class. So there is no point in building your own class library if the language provides one with suitable classes for your design. Okay. And if you want extra compile time, error checking, use a strongly typed language. Okay, very important. If you want to, if you want extra compile time, error checking, use a strongly typed language. If memory usage is convoluted in your application, then consider languages which provide automatic garbage collection. So if you require persistent data accessible by multiple users, then you may want to consider an object-oriented database. Unless a language is exceptionally clumsy to use, syntax should only be a minor consideration. So these are the some features of the object-oriented languages. So here we have listed some features of the object-oriented languages. So it supports for multiple inheritance, the class library, efficiency. Fourth one is strong typing versus weak typing. Fifth one memory management. Sixth one encapsulation. Seven packaging. Eighth one development environment. Ninth metadata. Tenth one parameter. The last one is the data persistence. Okay. The in detail we are going to study the one by one, but here we have listed the 12 object-oriented language features are there. The definitely the question may be asked on this one. List and explain object-oriented language features, multiple inheriting one, and data persistence. Okay. Now, what is the multiple inheritance here? How it supports for the multiple inheritance? We will see that. So there are some languages such as C++, class, Eiffel, and DSM support multiple inheritance. Okay, many others do not. And if the language you select supports multiple inheritance, there is a direct translation from your design to implementation. How much it is a easy part. So if the language you select supports multiple inheritance, there is a direct translation from your design to implementation. So the multiple inheritance introduces the possibility of conflict among attributes and operation names. Okay. Multiple inheritance introduces the possibility of conflict among attributes and operation names, and the classes could have more than one ancestor with the same attribute. And there are several approaches that languages take to solving the problem. For example, The Eiffel compiler rejects programs with such clashes. The class, on the other hand, has a protocol for resolving them, and in many cases, we strongly recommend that you avoid such conflicts. And relying on the compiler to resolve conflicts is a matter of poor style because it damages extensibility and can lead to confusion. That part we need to consider here. The confusion should not be there. The second one, the class library. So what is the class library and how it is going to support, that we will see here. So the most object-oriented languages include a library of useful generic classes, which may be used as is or customized to meet a specific need through the creation of subclasses. Okay, and the availability of a class library means that many components need not be re-implemented by the programmer. See, very important. What is the use of the class library here? The use of the class library is that the availability of a class library means that many components need not be re-implemented by the programmer. So it achieves the cost of the writing the code for the components. Okay, and the most useful kinds of classes implement general purpose data structures such as sets, dynamic arrays, lists, queues, stacks, dictionaries, trees, and so forth. And these classes often referred to as container classes. Okay, the library classes are also called as the container classes. So these classes, often referred to as the container classes, serve as a framework for organizing collections of other objects. Classes implementing various kinds of associations should also be available in the class library. Okay. More complete class libraries might include device independent abstractions of interface classes such as streams, input devices, display devices, file systems, or concurrent processes. A separate library of user interface classes for use with one or more windowing systems is useful, as is the graphics library. A support for string manipulation is needed by most programs. Okay, this is about the class library. And the third one is about efficiency. So how it could be the efficiency. So the each class has a structure containing methods accessible by objects of the class, and a pointer to each method is stored at a known location with the structure. A pointer to the method structure for the class is stored in each object. The runtime method resolution is performed by retrieving the method structure and indexing it by the known offset of the method. So this technique cannot be used if new methods can be created at runtime because the structure cannot be pre-computed, or if the name of a method can be constructed at runtime because the offset cannot be pre-computed. A language system can further optimize method resolution to use dynamic lookup only where it is needed. A large percentage of the method calls in a typical application can be statically bound by the compiler if it is provided with enough information. So there are two ways the compiler can acquire this information. So the one way is for the programmer to declare which operations may be overridden, thus limiting dynamic binding to only those functions. And the virtual functions of class and the generic functions of class reflect this approach. And the other approach is to provide a final optimization pass that analyzes the application as a whole, decides what methods are not overridden, and then recompiles the application taking advantage of this information. So this approach is adopted by the Eiffel language system. Note that the declaration of types for variables allows the compiler to be much more precise in its determination of which method calls can be optimized. Okay, this is about the efficiency. Okay. So the efficiency we have studied that. So what is the efficiency? Now the fourth one is the strong typing versus weak typing. So we'll see that what is the strong typing and weak typing. So object-oriented languages vary greatly in their approach to typing. So the term refers to whether each variable and attribute value is merely known to be an object, that is called as the weak typing, and or may be declared more precisely as belonging to a particular class or one of its descendants. This is called as the strong typing. Okay, and for example, the attribute, for example, the attribute radius is declared to be of type length. Then Smalltalk is a weakly typed language. All variables in Smalltalk are objects in unspecified class, and Eiffel, DSM, Objective-C, and C++ are strongly typed languages. The class and Objective-C support strong typing but do not require its use. A variable that references an object may optionally be declared, and the compiler will check usage of that variable. So the hybrid languages such as DSM, C++, and Objective-C even permit an attribute to assume a value which is not an object but rather is an underlying C language type. So the permitting non-object values increases efficiency of common operations such as arithmetic at some cost in uniformity of references. Now, strong typing in a language serves two purposes. The first one is strong typing provides the active support to the programmer in detecting mismatched method arguments and assignment statements. Okay, and strong typing also increases opportunities for optimization. The optimization is refers to the code. Okay, we need to reduce the size of the code, so that is called as the optimization. And the strong typing also increases opportunities for optimization, and the compiler can detect when a general purpose operation can be replaced by a specific function call. So no power is lost. No power is lost by the use of strong typing. The programmer can always declare everything to be of class object to get the same effect as a weak typing. Although weak typing is flexible and powerful, it permits dangerous coding practices. Modern programming language theory has been evolving in the direction of strong type checking, and much of the advances in the programming language theory have derived from restricting the programmer's ability to perform dangerous operations. And most new languages support strong typing. The premise behind strong typing is that it is easier to detect and correct software bugs at compile time rather than at runtime. And strong typing improves the reliability of delivered software. Okay, this is about the strong typing versus weak typing. And what is the memory management? So the memory management is that So the freedom with which objects can be created and accessed causes a problem when memory space must be reclaimed. The very important statement is that the freedom with which objects can be created and accessed, it causes a problem when memory space must be reclaimed. And most object-oriented languages allocate memory from a heap rather than using fixed blocks of global memory or a stack. And a dynamic memory allocation system can run out of memory unless objects that are no longer needed are deallocated. The principal problem lies in determining when an object is not needed or can no longer be accessed. The severity of the problem depends on the type of application and the memory architecture. The many programs that have access to a large amount of virtual memory can simply ignore the problem. And on the other hand, a highly interactive application expected to run indefinitely to mistaken consider memory management no matter how large the available memory space. And in this way, there are two approaches to memory management. Either it is done automatically by the runtime system of the language, or it is done explicitly by deallocation statements written by the programmer here. So the preferred approach or the automatic memory management relieves the programmer of the responsibility of deciding when to deallocate memory and avoids the risk of dangling object references that explicit deallocation is vulnerable to. However, users are understandably dissatisfied with some garbage collection schemes that result in long pauses at unpredictable points during execution. Incremental garbage collection schemes avoid long delays but impose a higher average cost, and it improved garbage collection algorithms offer some hope in this area. So the class and small talk section, and C++ requires the programmer to deallocate unneeded objects, but the C++ language allows the programmer to define a destructor functions which are called automatically when a variable goes out of scope. And this gives the programmer a convenient way of organizing and invoking explicit storage deallocation, but is not a garbage collector. So the dynamically allocated object must be explicitly deallocated by the delete operator. So the explicit deallocation runs the dual risk of deallocating objects that are still referenced, leading to program crashes, and failing to deallocate objects that are inaccessible, leading to memory waste, but it does not impose any additional time or memory costs on the program. Now the next point is about the encapsulation. So we'll see that what is the encapsulation. So the encapsulation is also called as the information hiding. So it consists of separating the protocol, the external aspects of an object that are accessible to other objects, from the internal implementation details of the object which are hidden from other objects. Okay. The encapsulation prevents a program from becoming so interlaced that a small change has massive ripple effects. You can change the implementation of a class without affecting its clients. You may want to change the implementation of an object in order to improve performance, fix a bug, consolidate code, or port it to a different system. Encapsulation is not unique to object-oriented languages, but the ability to combine data structure and the behavior in a single entity makes encapsulation cleaner and more powerful than in conventional languages that separate data structure and behavior. So the languages differ greatly in the degree to which the class boundary is enforced. Already we are familiar about this encapsulation. So encapsulation is not unique to the object-oriented languages, but the ability to combine data structure and behavior in a single entity makes encapsulation cleaner and more powerful than in conventional languages that separate data structure and behavior. So the languages differ greatly in the degree to which the class boundary is enforced. One way that encapsulation can be violated occurs when code associated with one class directly accesses the attributes of another class. Okay, and direct access makes assumptions about the storage format and location of the data. So these implementation details should be hidden within a class. And for example, an attribute value may actually be computed from other information. So the proper way to access an attribute of another object is to ask for it by invoking an operation of the object rather than simply taking it. Many languages such as Smalltalk forbid direct access to the attributes of another object, or as in C++ and trellis all permit attributes to be declared either public or private. The Eiffel provides perhaps the finest control of encapsulation through its expert statement, which lists attributes that may be read and operations that may be executed. The C++ print declaration allows limited loosening of encapsulation for access by specified classes or of functions. So the encapsulation can be violated through careless use of inheritance, and a subclass inherits the attributes of its superclass, but if the methods of the subclass directly access superclass attributes, the encapsulation of the superclass is defeated. The clause all Eiffel and C++ permit a class to restrict its visibility from its subclasses. There are arguments in favor of allowing a class to access its superclasses, but the cost is a tight binding between the classes. Okay. Often it is useful to write some private operations that are for internal use only by other methods of the same class, and is desirable to restrict the visibility of these operations that other classes cannot use them. It is often necessary to allow subclasses to access these internal operations, so a simple distinction between public and private is not possible. So the some languages permit a third level of access to subclasses such as the C++ protected declaration. So now we will see the about the packaging. About the packaging, so the class is not an adequate structuring construct for large systems. So most object-oriented languages lack partitioning mechanisms for controlling visibility between classes. So we have suggested the use of modules containing classes as a structuring mechanism during analysis. A related problem is that object-oriented languages typically require that the names of classes must be unique, and often this is not the case when two or more applications that were developed independently are combined. For example, two designers working independently might define different versions of a class called symbol with different operations and semantics. The problem is similar to name classes in block structured languages. So in the Ada language and in a class, a repackage construct provides the means to structure a system into separate components with their own namespaces. And in Ada, names declared in the specification of a package are not visible outside the package unless explicitly requested. allowing control of both the namespace and inter-package dependencies. Entities that are known by one name outside the package can be renamed within. Packages may be nested, allowing an entire subsystem to be encapsulated within a well-defined interface. Object-oriented languages would benefit by the addition of packaging capability, and in particular the ability to nest the packaging components of a system allows better control of a visibility. So this is about the packaging. Now the next one is the development environment. So what is the development environment? We will see that. So the tools that are available for browsing. So the tools that are available for browsing and editing source code, compilation, debugging, system integration, and testing have a big effect on your productivity, and its support tools are especially important in object-oriented languages because of the difficulty of managing inherited and dynamically bound features in a large system. A browser allows you to explore the source code in a structured way, asking what classes are present and what operations are defined for each class. The compiler or interpreter is the most important implementation tool. Whether the language is interpreted, compiled, or translated affects the speed with which you can make small changes and test their effect. And so an interpreter allows more flexible debugging. So interpreted systems such as Smalltalk and Lisp allow an executing program to be stopped, edited to correct a bug, and resumed. Objective-C offers an optional interpreter in addition to the compiler. So the some compilers translate an object-oriented language to an intermediate languages such as C, which is then compiled. So the C++ language was first implemented by the translation into C, but true compilers are now available. Translation may pose problems for symbolic debuggers because they do not understand the original object-oriented code. In evaluating, the debugger find out whether it shows you the original object-oriented source code or the intermediate code, which may be harder to read. The debugger should be able to inspect attribute values and evaluate object-oriented expressions. Tools for system building and change control are essential for large projects but are also valuable for individual programmers. Consider whether the proposed language provides them or integrates smoothly with existing tools. System rebuilding can consume much time if a simple change in one module requires that client modules must be recompiled as well. So try to determine what kinds of change trigger recompilation of clients. The experience has shown that the use of conventional building tools such as Unix make is too crude for many purposes. The finer grained development environments are needed but are only recently available. Now this is about the metadata here. So what is the metadata? So the metadata is the data about data. So metadata that is present at runtime allows an application to reason about and possibly even change its own structure and capabilities, including the operations and object supports, the attributes it possesses, or the types of attributes. There are also more conventional uses of metadata, such as writing a generic procedure that prints or saves any object using the attributes, names, and types. Languages containing explicit class descriptor objects, such as Smalltalk and DSM, contain runtime metadata about classes. A class object acts as a template for the creation of new instances, and the class may also contain descriptions of the attributes and operations such as name, type, or arguments. For example, a complex number class might define a real part and imaginary part attributes, each of which is represented as a 32-bit floating point number. Of course, the designer of the system knows the metadata. So, of course, the designer of the system knows the metadata. So, in principle, this data could be embedded in the code. But if the design changes, say by adding a new attribute to a class, then all the code that depends on embedded data will become invalid. The use of metadata at runtime rather than at compile time allows the construction of extensible systems with generic procedures and abstract classes. that are reusable in unforeseen applications. Metadata also can be used to support data persistence or by programming support tools such as debuggers, browsers, and inspectors. So the parameterized classes or generics allow a parameterized template to be written that can then be applied in several cases that differ only in the types of the parameters. For example, a generic list class can be instantiated as a list of points or a list of integers. The generic add element method on the list implicitly depends on the type of element. So the local variables within the method have a generic type that depends on the instance. So the parameterized classes are present in the Ada language and in Eiffel. Parameterized templates have been proposed for C++. So this is about the parameterized classes. So the next point is that the assertions and constraints. So here we will take the 2 minutes break. So don't leave the room. Don't put your attendance. You please wait in the room, okay? Within 2 minutes again we will start our lecture. So welcome back. So we'll see the remaining points. So we saw the parameterized classes and now we'll see the 11th point, assertions and constraints. So the assertions and constraints improve the odds that the behavior of a class matches the expectations of its clients. We can do this informally by writing a natural language description of the desired behavior. But how can we be sure that the description will be understood in the same way or even read by another programmer who wants to use the class? Usually, there are a few critical assumptions about the behavior. So, assertions and constraints improve the odds that the behavior of a class matches the expectations of its client. So, I requesting you all don't put the roll numbers here. I written here don't put the roll numbers again. The Sonali Bosare have put the roll number. Okay, are you listening me, Snehal? Hello.
Yes, sir.
See, I'm saying here don't put your roll numbers. What happens? Repeatedly, you are going to put the roll numbers here. Then it is very difficult to mark your attendance, and your roll number appears many times. Okay. So that is the reason I am telling you that once I tell you that you put your roll number, then only you have to put the roll numbers. Okay. Otherwise, unnecessarily don't waste the time by putting the roll numbers. Okay. In the last 5 minutes, I will tell you that you put the roll numbers here so that easily I can mark your attendance. But now don't put the roll numbers. Okay. Be patient for some time. So the 11th point is the assertions and constraints. So the assertions and constraints improve the odds that the behavior of a class matches the expectations of its clients. So we can do this informally by writing a natural language description of the desired behavior. But how can we be sure that the description will be understood in the same way or even read by another programmer who wants to use the class? Usually, there are a few critical assumptions about the behavior of a class. Operation or method can be expressed mathematically. These assumptions take the form of assertions that must be true at particular points during execution, such as preconditions and postconditions, and constraints must be maintained or invariants that must always be true. So assertions should also be written into the software in a form that can be optionally compiled and automatically checked at runtime. So while this technique can be used in many languages such as the assert macro available in many C implementations, it is particularly well supported in the Python language. So the constraints can be more than simply conditions to be tested. They can be viewed as a way of expressing declaratively what might otherwise have to be written as procedural code. And a language system could understand constraints that are declared and ensure that they remain true by taking action at runtime to maintain the constraints. The Prolog logic programming language has such capabilities. It would not be surprising to see such constraint maintenance systems become widely available under object-oriented languages. Now the last point is about the 12th point, data persistence. So what is the data persistence that we will see here? So the all computer programs operate on data here. If you require data that persists beyond the lifetime of a single program execution, then you will need to use a permanent data store. There are various reasons for wanting persistent data. The persistent data may provide the easiest mechanism for passing data from one program to another. Then persistent data allows the same program to resume processing at a later date. So the data stores are often useful for historical or archival purposes. There are several approaches to providing persistent data services. For example, files, special purpose hardware devices, databases, and intrinsic language support. Some new object-oriented databases are especially convenient in their data storage services. To a large extent, such an advanced object-oriented database looks like an object-oriented language, except that the orthogonal property of persistence may be specified for data structures. Okay. The advantages and disadvantages of object-oriented databases relative to conventional databases. Okay. This is about the object-oriented language features are there. So there are total 12 object-oriented language features we have studied. The first one is about the multiple inheritance, second class library, third one efficiency, fourth one strong typing versus weak typing, then fifth one memory management, the sixth one encapsulation, seven development environment, nine metadata, tenth one parameterized classes, the 11th assertions and constraints, the last 12th one is the data persistence. Okay, this is about object oriented language features. Now the next point is about the object diagram compiler. So what is the object diagram compiler that we will study in detail? So in the background we will see what is the background of this object diagram compiler. The next one is the problem statement, again the analysis, again the system design, again the object design, again the implementation, and again the lessons learned. Okay. So what is the object diagram compiler background we will see here? The compilers provide a natural application for the OMT methodology. So the most compilers are batch programs that consist of one or more passes. The passes means the single pass, double pass, like that. So the each pass works towards the goal of transforming the input to the output. For example, a C compiler may accept an input file of ASCII characters, and successive passes may parse into tokens and abstract the intended semantics, generate a code, and then optimize code. And users expect that a compiler will carefully check its input during processing. The more errors the compiler can detect, the fewer errors will be encountered during a program execution. And this point describes the development of a compiler for object diagrams for bill of material applications. The compiler is a batch program that accepts an object diagram as input and produces a relational database management system schema as output. So the compiler input is limited to object diagrams of bill of material problems because of the special error checking built into the compiler. The compiler has served two purposes. The first one is it solved the immediate problems of the target applications, and it was an important milestone in our continuing work on automating the OMT methodology. So the object diagram compiler illustrates several concepts. The several concept, the compiler architecture consists of four passes that step through a series of internal models. So there are many relationships and functional dependencies within a model but few between models. So General Electric has several internal applications that configure product assemblies. The business practice for those applications is that the customer specifies product function, the manufacturer must devise a corresponding product. For example, a customer might order a lawn mower that it is lightweight, inexpensive and energy efficient. So the manufacturer may fill the order with a mower that has a 1 horsepower gasoline powered engine, 45 centimeter diameter aluminum deck, and non-mulching blade. So GE does not manufacture lawnmowers, but we use the lawnmower examples of for convenience. The list of parts chosen by a manufacturer to build a product is called a bill of material, that is BOM. BOM is a tree of the direct and indirect parts that compose an assembly. The literature often refers to bill of material as parts explosion problems. So the BOM are often printed out as indented parts list, where the indentation corresponds to the depth in the hierarchy. So the figure shows a sample bill of material for a lawnmower. The first value listed after each part type is the part number. Thus, lawnmower LM16G has engine E1, deck D16, and so forth. So part properties follow the part number. So the lawnmower LM16G, engine E1, single HP gas powered, piston P1, 5 centimeter length, 5 centimeter diameter, carburetor, that is the car B9, wires W15, quantity 4, oil resistant, that is the deck D16, 45 centimeter diameter, aluminum blade B16, 40 centimeter long, non-mulching, wheels WS3, solid rubber 8 centimeter diameter. So this chapter describes a portion of the new bill of material configuration system, a subsystem called the object diagram compiler. First, first we draw an object diagram of a BOM parts explosion within an ordinary graphics. editor by carefully placing many lines, triangles, boxes, text strings, and other primitives. The object diagram compiler then processes the object diagram and ultimately generates dbms commands that create tables and indexes. Whenever we change the object diagram, we return the compiler and generates the new dbms commands. Thus, the object diagram is a living document. Thus, the object diagram is a living document. The object diagram compiler simplifies documentation and dbms schema generation by using the same source document for both. Our success with the object diagram compiler has motivated further work towards developing more comprehensive tools for automating the OMT methodology. So this is about the problem statement. So the figure shows the objective of the object diagram compiler is to translate bill of material object diagrams into the database commands and check for input errors. So the BOM object diagram drawn with graphics editor statements, object diagram compiler, error messages, the database commands, and the data dictionary. So this is a diagram for the functional model of object diagram compiler. The compiler input, compiler output, miscellaneous requirements. So this is about the problem statement. So the figure shows the objective of the object diagram compiler is to translate BOM object diagrams into database commands and check for input errors. So this is about the compiler input, the lawn mower, mower number, mower width, blade, blade number, blade length, mulching, and the engine, engine number, motive, power, horsepower. Okay. The compiler must read an ASCII description of a BOM object diagram produced by a general purpose graphics editor. We used FrameMaker, but others such as MacDraw and Interleaf are also suitable. The graphics editor must be geometric, shape based, and not pixel based. The compiler input is analogous to the source code of a conventional programming language compiler. Figure is a sample BOM object diagram. A lawnmower has a blade and engine. Each blade and engine may be associated with several lawnmowers. Lawnmower, blade, and engine are described by attributes. So this is the compiler input. The object diagram compiler must support basic object modeling, constructs, classes, attributes, binary associations, binary aggregations, and generalizations. The compiler does not need to support object modeling constructs that are not needed for our BOM applications, such as qualified associations, ternary application relationships, and operations. Okay, the rectangles is the size of the rectangle, text line rectangle. Okay. So the compiler output. So what will be the compiler output? The compiler must produce a series of database commands. This output is executed as a script file to load a data dictionary, and we used the Oracle DBMS, but any relational DBMS that supports the SQL language is suitable. The compiler must generate association names and determine how to implement relationships. The compiler output is analogous to the object code of a conventional programming language compiler. The object diagram compiler stores its output in a data dictionary custom designed for BOM applications. Several downstream programs complete the process of creating the tables and indexes that store individual BOMs. We used this custom dictionary rather than the DBMS dictionary because we required BOM specific extensions. Now the miscellaneous requirements. So what will be the miscellaneous requirements? The object diagram compiler was subject to further requirements on development time and performance. The compiler had to be developed quickly in 4 months or less. So it was part of the larger BOM generation project, and we did not want to divert our attention. Our requirements on execution time were more lax. An execution time of 2 hours or less is adequate because the compiler is a batch program that is only run at system setup time. The compiler is not used for the day-to-day generation of BOMs. As it turned out, because of skillful software engineering, performance was much better than required. So the compiler must detect input errors but need not correct the errors. For instance, class names must be unique, have less than 31 characters, and begin with an alphabetic character. The compiler must not abort when it encounters user errors. The compiler must accept bad input and keep running so that the user can detect multiple errors from a single run. The compiler must tolerate imperfect connections. Since object diagrams are prepared with a general purpose graphics editor, it is difficult to align and precisely connect everything. And the compiler must accept input that looks correct when printed on paper. Also, the compiler must detect mistakes that are not visible, such as superimposed drawing components. The compiler must isolate dependencies on graphic editors and relational DVMS within one or two modules. Then the compiler can be ported without major rewriting. This is about the analysis of the object diagram compiler. So analysis is the first step towards solving the problem statement. So it quickly became apparent that the difference in level of abstraction between input and output was too great to span in a single step. So we decided that it would be best to use several passes. This conclusion is not surprising since many compilers require multiple passes. The disadvantage of a multi-pass approach is that the developer must prepare multiple object models and design multiple compilation phases. The advantage of multiple passes is that complexity is addressed in a divide and conquers fashion. The resulting code is easier to put since graphic editor and DVMS dependencies are isolated in small portions. Okay. Here is the input ASCII description of object diagram. So it parses the graphics editor language and it is geometry model. So extract connectivity, connection model, abstract BOM entities, internal meta model, generate database commands, and output is it commands to load database data dictionary. Okay. So the first one is the parse graphics editor language, geometry object model, extract connectivity, connection object model, abstract BOM entities, internal meta object model, and generate database commands. Okay. Now, what is the parse graphics editor language? So the first pass reads in the raw diagram FrameMaker file generated by the graphics editor and builds the geometric model. The first pass corresponds to lexical analysis in a conventional programming language compiler, and this pass required little analysis effort beyond figuring out a correct BNF syntax for the graphics editor language. Our development of a BNF grammar for the graphics editor was aided by vendor documentation. 3.2 is that geometry object model. So here you can see the geometry object model, how it is created. The page number, the ellipse, fill, rectangle, polyline, polygon, text line. So again the ellipse and rectangle they have the boundary, top location, left location, width, height. The polyline and again the polygon they are having the point x location and y location. The text line also having the point x location, y location, and the font is having the size italic, bold, underline. Okay. This figure summarizes the geometry model. We have omitted some classes, associations, and attributes in order to conserve space and simplify explanation. So the geometry model represents a diagram as a series of graphic primitives and is a convenient form for further processing. So the geometry model represents a diagram as a series of graphic primitives and is a convenient form for further processing. The geometry model regards an object diagram as simply a picture. The graphical objects, ellipses, rectangles, polylines, polygons, and text lines coexist but have no interrelationships. We derived the geometry model directly from the BNF grammar of the graphics editor language. So the graphics editor that we used organizes components by page. A text line is a single line of text that may be placed anywhere on a page. A text line has a font and alignment and originates at a point. The each font describes text size and special features such as italics, bold, and underlining. The geometry model includes page number for use in error messages. Ellipse, rectangle, polyline, and polygon capture graphical information in the object diagram. Ellipses have a location and a bounding rectangle. An ellipse may have a hollow fill or solid fill. Rectangles have a location, width, and height. Polylines and polygons are composed of straight line segments that connect a sequence of points. A polyline is an arbitrary sequence of lines. A polygon is a closed geometric figure. The geometric model for our lawn mower example contains the following objects: 6 rectangles, 11 text lines, 3 bold font yet normal font, 2 polygons, diamonds, 2 ellipses which happen to be circles with solid fill, and 2 polylines, vertical lines between lawn mower and blade, lawn mower and engine. Okay, this is about the sample BOM object diagram. Now, to extract the connectivity, the second pass consolidates raw geometry. It classifies sizes and shapes and detects intersections and attachments of geometrical primitives. We call the output from the second pass the connection model, and figure in the next slide represents part of the data flow diagram for this pass, and ellipses, rectangles, polygons, and text lines from the geometry model are input data stores in the functional model. Every class and association in the connection model is the output of one or more functional model processes. Recall that during analysis, we do not specify algorithm but specify the effects of processes. Okay. To extract the connectivity, so this is about the connectivity diagram. So in figure, groups of the contiguous rectangles are recognized as blocks, and groups of intersecting lines are recognized as nets. So each block and net intersection is found and stored as a node. So ellipses are classified into multiplicity balls or set cross references. So the each multiplicity ball is associated with the node, and each reference is associated with a block. So each text line is bound to its nearest block or net. So the connection object model. So this diagram is about the connection object model. So the page, reference, triangle, block, node, net, diamond. The connection model summarized in figure this. So bridges the geometry model and the internal meta model. Classes that are shaded are carried forward from the geometry model. Connection model regards an object diagram as a topology, a collection of blocks connected with nets. Blocks and nets have attached geometry and text here. So the block, net, and node classes form the core of the connectivity model. So each block has a name. A node corresponds to exactly one block and one net. So the each block may have many rules. Each net may have many nodes. A node may be connected to a ball or a diamond. A net may be connected to a triangle. A block may have several cross-reference circles pointing to other pages. Both blocks and nets have text. Okay. And the connection model for our lawn mower example contains the following object: three blocks named lawn mower, blade and engine, two nets named lawn mower, blade and lawn mower engine, four nodes, two diamonds, each associated with a node, and two solid balls, each associated with a node. The lawn mower block is associated with the two text lines, the mower dot number and mower width. Similar associations occur for blade and engine. So that is 3.5 abstract BOM entities. So the third pass raises the level of abstraction. The graphical symbols in a BOM diagram have more meaning than their mere shape. Okay. A block denotes a class. A net represents a generalization or association. Parse tree bands together cross references to classes, verifies uniqueness of names and classifies relationship types. Parse tree applies hard-coded rules for mapping relationships to tables. The second and third passes correspond to semantic analysis in a conventional programming language compiler. The functional model for this pass is complicated by extensive error checking. Much of this error checking derives from using a general purpose graphics editor to construct the input object diagrams. In general, the user can make many diagramming errors such as dangling association lines, duplicate class names and class blocks without a name. The object diagram compiler also checks for errors peculiar to BOM generation. The pass-through functional model is too large and complex to display here. Okay. So this is about the 3.5. We have covered this object diagram compiler. So the remaining points I think we will cover into the next session. Okay. So I want to say thanks you all. Very patiently you are listening my lecture from morning. So 4 hours continuously I took lecture. So thanks once again. So now you are allowed to put your roll numbers in the chat box, and you can leave the Google class. Okay. Thank you one and all.